Everyone, we're going to go through our second unit now. We're going to start talking about matter. Today's notes that we're going to cover are classifying matter notes. So you can find this PowerPoint on our class website as well. So just to start with, there's a lot of vocabulary in this unit. These are the terms that you're going to need to know. You don't have to write them down right this second, but you're going to notice that all of these terms are throughout the PowerPoints and they will be in bold. So as you get to those words, you're going to want to make sure you document those words. It's not just a matter of knowing definitions for this unit, but you're going to need to know how to, what they really are and how you apply them to actual chemistry. So we're going to use the term solution a lot, and it's not the answer to the problem. It's a type of mixture, and you're going to be describing solutions a lot in chemistry later on. You're going to need to know how to classify between a suspension and a colloid. You're going to need to know what it means to be a heterogeneous or a homogeneous mixture. You're going to need to know how to use the different types of separations like filtration, chromatography, distillation. So it's not just a matter of memorizing definitions here. Okay? Alright, so let's get started. Chemistry is a study of what? Well, it's a study of matter. And matter is anything that takes up space and has mass. So right now, maybe stop the movie and start listing out what are some types of matter that you know of. So in class, we often will throw things out like the desk, the kid sitting next to me, air. All of those things take up space and have mass. Light and sound are actually not matter, which is good because the sound that you're hearing is not crushing you. Light is kind of a confusing one because light acts like it has mass and yet it is a photon. So it's very confusing for that one. Okay, so you can make your list. Alright, matter is made up of atoms. Yeah, so atoms is a unique term. It came from Democritus, who was a Greek philosopher around 450 BC, so that's a long time ago. He came up with this word called atomos, and atomos meant that it was the smallest particle. It was indivisible. So it came from this. He was doing a thought experiment, Democritus was, and he was thinking about, can I take a piece of something and cut it in half over and over and over again? And at some point, am I ever going to get to a piece where I can't cut it in half anymore? And he said, okay, well, the smallest piece that can't be cut in half anymore, that's called an atom. We're going to learn in the next unit about how that theory of the atom kind of developed over about 2,000 years. Alright, so what does an atom look like? Well, it's kind of hard to see. You can't really see atoms because they're too small to see with the eye. But we can use these things called a scanning tunneling microscope or an SEM, a scanning electron microscope, where they use beams of electrons and the beams of electrons bombard some material and then it starts giving you a shape. Well, this is actually an STM image of just a single zigzag chain of cesium atoms. So these are the cesium atoms, boom, 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 on a gallium arsenide surface. So this is the gallium arsenide surface, and you can see that there's one layer up is the cesium atoms. There's this really cool video about whether you can actually see an atom, and it shows you more in depth. It's about a 5-minute video, pretty helpful. We can see groups of atoms really well. Look around your house right now. Everything is made up of atoms. Here's some kind of fun STM images of people can make these surfaces or coat to the surface with just a single layer of atoms, and they can make fun little shapes. In the video you'll see that IBM actually wrote out its name, IBM, in just a single atom, so it's kind of cool. Alright, so groups of atoms, when we put atoms together, we call them elements. And elements are when you have identical atoms grouped together. Now you could have them as single atoms grouped together, and that would be like sodium, metal, different atoms like that. You could also have two atoms of the same element bonded to each other, and this would be like hydrogen. Hydrogen comes as this thing called a diatomic, it comes as H2. You don't have single atoms of hydrogen just floating around in the atmosphere. It's naturally bonded together. So anything on the periodic table is an example of an element. Calcium, hydrogen, fluorine, rubidium, etc. I haven't mentioned this yet. Oh, yes, I have. You want to start memorizing those elements and their symbols. Don't forget. All right, so here's some other pictures. We've got copper and aluminum. Those are both elements. All right, what if we take different elements and combine them? Then we're going to call them a compound. A compound is essentially that. You have different elements that are bonded to each other. So now I have different shading showing you two different elements. You can also show it like this where there's the little rod in between. There is no actual rod holding two atoms together. This is just a model to demonstrate what a molecule looks like. Not actually there. Okay, it's more like this first picture where it's overlapping of the atoms that creates the bond. So, example of compounds, well, they're not going to be on the periodic table, but it's anything that has a chemical formula. Okay, so I'm going to say that again because I don't think it's on my slide. A compound is anything that has a chemical formula to it. As long as it has a single chemical formula, it is a compound. They're not mixtures. So water, H2O, that is not a mixture if you're considering pure water. Its formula is H2O. Now the water you get out of your tap, it's a mixture. There's other junk in it. Okay. Alright, so here's another example. Sodium chloride, or table salt. It's made up of sodium atoms and chlorine atoms. And you're going to notice this is actually the structure of sodium chloride. It's kind of an interesting structure because it's not just one single sodium atom and one single chlorine atom. It's a whole bunch of them, and they're all alternating. So if you look at this little gray circle here, or sphere here, it is attached to 8 or 6 other chlorine atoms. You look at this green chlorine in the middle, it's touching 6 other sodium atoms. So each of those atoms is actually bonded to a whole bunch of other atoms. And that's why it's so stable. It's why it's going to sit on your shelf for 20, 30, 50, 100,000 years. And it's not going to change its chemical formula. Alright, so let's take a second and do a little bit of formative assessment here. We've got identify these pictures as either elements or compounds. So what you're looking for is what kind of element do you have and how are they bonded? So pause the video and identify. Is it an element? Is it a compound? A mixture of elements, mixture of compounds? Alright, so this first one, I see that there's 2 yellow circles attached. That's going to be the same atom there. That means since there's no other element in here, this must be just an element. There are multiple units of this particular molecule, but it's not a compound because you don't have a different element attached. In this one, jar B, you've got the gray and the yellow attached into one single unit. So these must be compounds where there's 2 yellows and a gray. This kind of looks like H2O. This next jar, it does have the 2 different elements, but they're not bonded to each other. So the yellows, that's an element, and the grays, that's an element. So you actually have 2 different elements in here. And the last one, same as the jar C, except now the jar has a different proportion of yellow to gray. So we've got 1 element in this jar, 1 compound in this jar, 2 elements, and 2 elements. Alright, pure substances. What is a pure substance? What does it sound like to you? It sounds like something that's pure, right? It doesn't have any impurities in it. It's one single thing in that substance. A pure substance cannot be separated without changing identity of the compound or of that substance. Elements and compounds are pure substances. If you look in this box here, you see that it's the same atom attached over and over and over again. That's an element, and that might be hydrogen, it might be oxygen, it might be nitrogen. That is an element. A compound is when is a pure substance because now you've got these 2 elements that are bonded to each other, and each unit is identical. So there's no separation that can happen without changing the identity of this substance. Now, mixtures, on the other hand, can be separated. So mixtures, you can see from these two pictures, you have trail mix. I don't know if you're like me, but I always pick out all of the M&Ms. And then I'll go for the cashews. And then I'm pretty much done. So you can easily, mechanically separate a mixture. Now, well, I'll take that back. It's not always easy. Trail mix is easy to separate. You know, the different color Skittles are easy to separate. But if you're looking at your tap water that you have coming out of your tap, there's a huge system in place that is cleaning your tap water so that it's healthy and safe for you. The department, or whatever, the water utilities, they spend a lot of money and a lot of time cleaning out the water, but it can be separated, the junk from the good stuff. Okay. So in this picture over on the right, you can see that the red and the black are actually two different substances, maybe two different elements, and you can separate out the black from the red. So atoms, molecules, compounds, mixtures, we can represent them using these different colors, and you're going to see representations in your homework, and you're going to be expected to identify based on what you see. Okay, well this is two different elements that are bonded to each other. This must be a compound. This one has a singlet, and this one has the two blues together, and this one's got that compound again. So this is definitely a mixture of elements and compounds. You need to be able to recognize what those pictures are representing. Alright, so let's look at this one. We've got identify as a pure substance or a mixture. So in the jar A, we already identified that it was an element in the first set. So if it's just an element, it must be a pure substance. In this jar, we identified this one previously as a compound. Well, what's a compound? Can you separate the gray from the yellow? Not without changing the identity. So this is actually a pure substance as well, even though it has two different elements. In this jar, the two elements are not bonded. So you can actually pick out all of the gray molecules from the yellow molecules. So this one's a mixture. And then jar D is also a mixture for the same reason. Okay, so we have our pure, pure, mixture, mixture. And these were our previous classifications. Alright, so I wanted to show you what you can do with your homework now. You're able to now complete the elements, compounds, and mixture worksheet in your homework packet. So this is what it looks like. In that first section, it says that elements and compounds can be written as a chemical formula. So all the elements, those element symbols, those have a chemical formula. That is the chemical formula. Mixtures, however, don't have a specific chemical formula. So what you're going to do is classify the following as element, compound, or mixture. And I've asked you also to give a reason why you would say that. So for the first one, argon. Have you ever heard of argon? Well, it's actually on the periodic table, so it is an element. And my reason would be on the periodic table. Easy as that. Okay? Down here, in this section, you're going to be classifying each of the pictures. So you're going to look at each of these and say what is inside that picture. So let's do this first one as an example. This first one has the black and white circles are representing different elements. I see that there's the blacks are on the outside and the whites are in the middle, and then we have the whites on the outside and the black ones in the middle. So these are two different molecules. They are not the same. They're bonded differently, even though you've got the same number of atoms within the compound. So because there are two different molecules or two different compounds, I'm going to call this D, mixture of compounds. Okay? So that's how you're going to do your homework. Back to this. Let's talk about mixtures for a little bit. Mixtures are pretty interesting. There's an entire field of chemistry called analytical chemistry, and the purpose of this field is to really classify mixtures and separate mixtures and identify what is in those mixtures. I remember having a professor in college who said that one of his projects in analytical chemistry was to take a Barbie doll and separate it out into all of its different components. If you think about all the different molecules that are made into a Barbie doll, like, I was horrified at the thought of having that as a project, especially because I love Barbies. Okay, types of mixtures. So we've got two different types of mixtures. There's homogeneous mixtures and there are heterogeneous mixtures. Homogeneous mixtures just means that all of the components within the mixture are evenly mixed or evenly distributed. It has nothing to do with how much of each of the components is in it. It's just how are they mixed. Can you tell the difference between the components within that mixture? If you look at apple juice, you pretty much can't tell the water from the sugar, from the maleic acid, all the other things that are in apple juice. You can't tell what's in it based on looking at it. You can just see that it looks pretty much the same throughout. Okay? Heterogeneous mixtures are an uneven distribution. In this rock, you can see that there's different colors, and those different colors represent different minerals that are made up into that rock. Now, that seems like an easy classification. We're going to go into more on this heterogeneous mixtures in a bit. So let's classify these mixtures further. So the first kind is the solution. Not the solution to a problem, no. The solution, which is a homogeneous mixture. Solutions have very, very, very small particles dissolved up into a solvent. So you can see down here it says solute are those small particles that get dissolved. Solvent is the liquid, the solid, or the gas that does the dissolving. Often we think of solvents as a liquid. They don't have to be a liquid. It can be a gas or a solid. There are such things as solid solutions. We'll talk about that in a second. Those very, very small particles are so small that you really can't see them in the solution. The particles do not settle out over time. If you think about Kool-Aid, when you take the Kool-Aid powder and you dissolve it up, you stir it, and eventually all of it goes away. Well, that's a solution. Oh, if you let it sit over time, it would probably still be all in solution. Now, sometimes your juices, you might have stuff settle out, and that's because some of those particles are a little bit bigger, and that wouldn't necessarily be a true solution. This last piece, no Tyndall effect. Tyndall effect is this picture up here. You take the substance in a jar, and you take a light and you shine it through the mixture. Tyndall effect is when the light shines through the mixture, and if the particle sizes are big enough, the light can be scattered. So you notice in this jar on the right that the light is kind of bouncing off the particles, and you're seeing it come out to the side. Whereas in the jar on the left, the light is going right through, you're not seeing the light scatter. So when solution, because they have very small particles, they should have no Tyndall effect at all. Okay. Alright, so another example of a solution is isopropyl alcohol. If you go into your bathroom, if you have alcohol in your closet or in the medicine cabinet, it says it's an alcohol solution. This one is pretty fuzzy, but maybe it says 70%. So there's isopropyl alcohol in here, and then the rest of it is water. Well, because it's 70% isopropyl alcohol, the solvent is the isopropyl alcohol, and the water is actually the solute. Just kind of hard to think about. Most times, water is the solvent. Regarding the solid solutions, there's such thing like if you think about alloys, we can maybe call those solid solutions because they're different mixtures of elements. And then gas solutions, well, look around. All that air, that's a gas solution. Nitrogen is the biggest component, and everything else is dissolved up in the nitrogen. Alright, so some more special mixtures. Now we're getting into heterogeneous. We have suspensions. Suspensions are heterogeneous mixtures that have very large particles, and those particles eventually settle out. And if you've got it sitting out, it might take a while, but they eventually will, all the pieces will settle out, and the solvent will look clear or see-through. Suspensions do have a Tyndall effect because that light is able to scatter off those really large particles. Some examples: fresh squeezed lemonade, that's a suspension. If you've got the pulp, all that pulp is eventually going to squeeze out, or sorry, settle out. Mud, if any of you have ever gone down to the river, gotten a scoop of water, any of those, there's silt and dirt and rocks and all that floating around in the water. Eventually, if you let it sit on your countertop for like a week, it would settle out. Our last type of special mixture is called a colloid. Colloids are kind of confusing sometimes. They are heterogeneous, but they're medium-sized particles. And you might be thinking, okay, we talk about small particles, we talk about large particles, now medium-sized. How do I know what's medium? And I'm not going to ask you to memorize any specific size of particles. It's just relative, so colloids just have relatively smaller particles than solids or suspensions, but relatively larger particles than solutions. So they're evenly dispersed throughout another substance, so it's kind of like a solute-solvent deal, only the particles are not actually dissolved. It does have a Tyndall effect, and sometimes to the point where you can't actually see through the substance. Like milk is an example of a colloid, but if you tried to shine a light through a bottle of milk, it would be pretty difficult. The particles don't settle, and that's what makes them different from suspensions. So if the particles settle out, it's a suspension. If they don't settle, then it's a colloid. Some examples of colloids would be milk. Milk has a lot of different molecules in it. There's fats and proteins and sugars, and some of those larger particles just don't settle out, or they don't really mix well, and they're too big for light to get through the whole solution. So one caveat: milk does eventually have this sediment that goes to the bottom if you let it sit in your fridge for 6 months. Don't ask me how I know that. Mayo, also considered a colloid. Blood is a colloid. There's lots of larger particles inside blood, but they don't settle. Alright, so do some practice questions. Maybe take a minute, pause your video, and identify what kind of mixture each of these substances are. Alright, so we have shaving cream. Shaving cream is kind of interesting. Shaving cream is usually under pressure inside the can, and when you release the pressure, then air particle, like when you turn it, push the button and it lets it out, it typically expands, and the pressure is changing the size of the bubbles. But shaving cream, it's kind of a colloid. You can't see through it very well. Light scatters. It's not really going to settle though, so we consider it to be a colloid. That's why these colloids can be kind of difficult. Muddy water, that was our example in the notes just a second ago. Muddy water, when you take that muddy water, it'll settle out, so it makes it a suspension. Fog is kind of a controversial one. I usually have students who say it is all three different types of mixtures. Well, I know it's not a solution because when I'm driving through the fog, which I had to do a few months ago for all the way to Toledo and back, I couldn't see through the fog very well because my headlights were scattering, the light was scattering, and I could see nothing. So I know it has to be some type of heterogeneous mixture. Now you have to decide, do the particles settle or not? Well, some think they do, and I would tend to disagree. So fog is typically, you've got essentially a cloud is forming low enough in the atmosphere that it's down at ground level. Usually the reason fog goes away is because the heat of the sun evaporates the water and causes it to disperse. So I don't think it's necessarily settling out. It's more just drying up or warming up and moving along. There is dew that is on the grass, but that dew, I would say, is more because water condensed onto the leaves, which were cold. So I'm going to call it a colloid, and I think others agree with me if you would do some research on it. Salt water, if you put salt in water, it completely dissolves. I would call that a solution. And then Italian salad dressing. unless I want a whole bunch of oil and nothing else, I better shake it up. So it's probably a suspension. Alright, here's a flowchart that you're going to want to pause the video and copy out into your notes. This is pretty important for identifying what kind of matter you have. So let's go through it. Matter, if it takes up space and has mass, then it's matter. Now you would maybe ask, can you separate the matter out? Well, if yes, it's going to be a mixture, and if not, then it must be a pure substance. So let's go down the pure substance lane for a second. So this matter that cannot be separated is a pure substance. I would look at, are the atoms identical? If yes, then it's an element. If not, it's a compound. Maybe you have a chemical formula that you can use. If the chemical formula is just one single element, subscript or no subscript, it's going to be an element. If the atoms are different, like sodium chloride, NaCl, that must be a compound. Alright, back to the mixture side. It can be separated. You might look at, are the particles evenly distributed? Can you see through it? Is it something that you can tell the different substances involved? If yes, the particles are evenly distributed, it's a homogeneous mixture, aka a solution. If the particles are not evenly distributed, it's a heterogeneous mixture. Well, now we need to ask another question to get between suspensions and colloids. Can you think of what question you would ask? I would say, can the substance, or does the substance settle out over time? If yes, it's a suspension. If not, it's a colloid. Alright, so you can use this flowchart to help identify what kind of substances you have and be able to work with them from there. Alright, so using that flowchart, here's a whole list of items that you would want to classify. So maybe take a minute, pause your video, and identify, is this an element, compound, a mixture, what kind of mixture is it, solution, colloid, suspension, etc. Alright, so this first one I would classify, sorry I clicked it too early, it was an element. Palladium is on the periodic table. The element symbol is Pd, so it is definitely an element. Smog. We don't have that big of an issue of smog here in Columbus, but smog is usually, you've got all kinds of nasty junk that is in the air, and usually it's because there's some larger particles that are causing what we call nucleation sites, so water can attract to it. There's a whole bunch of different gases, a whole lot of nasty stuff. Definitely, I would say heterogeneous mixture because light will scatter, it causes haze. The question is whether the particles actually settle out. If they do settle, most likely there's some settling with dust and nasty stuff all over your car. If you work in or you live in a city that has a lot of smog, your car is going to get really nasty. Your house is going to have junk all over it, so maybe call that a suspension. Ethanol. Ethanol is a kind of alcohol. It has a chemical formula of CH3, CH2OH. So ethanol, since it has a chemical formula, the chemical formula is made up of carbon, hydrogen, and oxygen. It's a compound. Paint. Paint is not on the periodic table. There's a lot of different compounds within paint, so it's definitely a mixture. If you consider the different kinds of paint, some paints you have to shake up, sometimes you don't. House paint, you have to stir it before you use it because particles have settled out. I think that's what I've based this one on. You can call it a heterogeneous mixture because of the larger particles inside, and it's a suspension, most likely. And then last one is soda pop. Some of you, I'm sure, love soda. Soda is, you have all kinds of stuff in it. There's carbon dioxide dissolved up in the water. That makes it fizzy. There is sugar galore. There are different flavorings. There's maybe food colorings. There's preservatives of sorts. But you usually can see through it. If you consider before you open that pop bottle, I'd say that's probably a solution. Alright, so you've made it through all of these notes. Now you can work on classifying a matter worksheet, which is the next page in your homework. So you see that in the instructions it says, classify the following as a pure substance or a mixture. So you're going to either circle one or the other, just like in the example. And then tell whether it is an element, a compound, a heterogeneous mixture, or homogeneous mixture by writing that in the blank. You can even go further with the heterogeneous and identify it as a suspension or a colloid. Sometimes they might be a little bit complicated, but do your best. So here for the example, salt water. Not a pure substance, so it's probably a mixture. It's got salt and water in it, so we circle a mixture. Further classification. As a mixture, salt water, typically the salt is completely dissolved in the water. You can't really see it, so it would be homogeneous. And because it is homogeneous, it has to be a solution. We didn't have any other special classifications. So this answer works because salt water is made up of water and salt, so it's a mixture and it's completely dissolved, so it makes it heterogeneous. That's exactly what we just went through. So you're going to do hand sanitizer, zirconium metal, isopropyl alcohol, and chocolate milk. Yummy! Second section, you're going to identify solutes and solvents in each solution below. So notice that some of these might be solid solutions and gaseous solutions that we talked about. You're going to underline the solutes, so the thing being dissolved, and you're going to circle the solvents. Remember that a solute dissolves the solvent, so usually that solute is in smaller proportion. Okay? And then there's several questions below. Read through them. This number 14, you're going to draw a picture. Make sure that you are very clear with how you're depicting the solution, the suspension, and the colloid. Alright, that's the end of this video. Best of luck, and I hope to see you back at school soon.